Okay, so in the last class we were discussing the Riemannian geometry, and we discussed the metric on two sphere S2, and we wanted to, of course, know how is it that the metric on S2 is different from the metric on a, say, Euclidean space. Okay, Euclidean, by Euclidean I really mean flat space. Okay, so we need to have a criteria which would allow us to distinguish certain invariants which are maybe non-zero for S2 and zero for, say, flat space, or other way around. Any which way you could, you basically need only the distinguishing criteria. Okay, and of course this distinguishing criteria should be independent of choice of coordinate systems. Otherwise, in one coordinate system they are the same, in another coordinate system they are different, then we really don't have an invariant statement to make as to whether these objects, whether these geometries are different or not. Okay, so we decided that the relevant quantity should be scalar quantity and the general coordinate transformation, and we want to construct a scalar out of the metric, because metric defines geometry on these spaces. Okay, so this was our conclusion, that we should have a 0, 0 tensor which is a scalar, but it should be constructed out of the metric defined on the space. Okay, fine. So so this is the thing I just said, that if it is different from different spaces, then we know that these geometries are different. Okay, so so the simplest thing that we can think of is just contraction of the metric components, and but that is trivial. It is independent of any choice of metric, so it doesn't matter. Yes. Is there a question? Okay. So so clearly this choice is not interesting, because G alpha beta would give you answer 4, no matter what value, what components values G alpha beta would be. Okay, so it's kind of useless to use this as a criteria. In fact, anytime you use only metric and not its derivative, it would always land up with some constant quantity, and it is not going to be very useful. Okay, so we therefore need to construct tensors uh, out of metric and its derivatives. Okay, and with that understanding, we considered first partial derivative of the metric, which was d alpha g beta gamma, and d alpha g beta gamma has a transformation property which is not like a tensor. It has a piece which looks like a tensor, but it has a piece which is kind of which looks like a inhomogeneous piece. Okay, it's not exactly inhomogeneous in the sense that, like, it does contain g beta gamma inside it, but nevertheless, you know that g beta gamma can be just used to raise and lower indices. So therefore, this piece would look very much like a inhomogeneous piece. Okay, so but nevertheless, definitely a tensor wouldn't have a piece like this. It would have had only the first row of this transformation. Okay, so in that sense, we know that partial derivative of g beta gamma is a quantity which is not a tensor. Okay, fine. Now, if it is not a tensor, then of course we cannot construct a tensor out of it. So as far as our search for an invariant object is concerned, this is a place where we cannot really use anything to construct a quantity which should be frame invariant. Okay, but nevertheless, this partial derivative teaches us something else. Okay, we can write down a new quantity which I defined last time as the Riemann-Christoffel connection. And the Riemann-Christoffel connection is written like this: half of inverse metric G alpha delta, where alpha is this index on gamma alpha beta gamma, but delta is summed, of course. So partial derivative with respect to beta of G gamma delta minus partial derivative with respect to gamma of G beta delta minus partial derivative with respect to delta of G beta gamma. Okay, so this is the way you write down this gamma, alpha, beta, gamma, and it, it was an exercise for you last time that you check that under coordinate transformation that G alpha beta transforms like a second rank covariant tensor with downstairs indices, and G upstairs is of course a second rank contravariant tensor. Using those properties show that the Riemann-Christoffel connection transforms inhomogeneously in this particular fashion. Okay. Remember, we had defined some gamma. I'm using the same notation gamma because they are actually related. We have used the earlier definition of gamma, which was only this piece. Okay. So, but that piece was constructed purely out of general coordinate transformations, and whereas general coordinate transformations relate one uh, frame to an equivalent frame. Okay. On the other hand, the metric G alpha beta is the one which parameterizes a space, and if G alpha betas are different, then it is likely that those spaces could be different. Of course, they may be same if two G alpha betas are related by general coordinate transformation, obviously. But to give an invariant definition of a connection, it is better to use metric than use general coordinate transformation. Okay, so you can check that this is the definition written in terms of geometry, which transforms exactly the way earlier gamma alpha beta was defined uh, in the class. Okay, so this is the transformation property. Fine. So since gamma alpha beta gamma is not a tensor, we can kind of check that the non-tensorial property of the first derivative and the non-tensorial property of gamma alpha beta would be kind of, one can check that they are related. Okay, for that all you need to do is to kind of push this derivative in and see that there is a second derivative piece sitting around, okay, which is kind of related to a second derivative piece here. Yeah, all you need to do is to arrange this quantity in such a way that you don't have multiple such second derivative pieces. Okay, fine. So of course the problem with non-tensors is that in one coordinate system there could be zero, in another coordinate system there could be non-zero. So you cannot use objects like this to give an invariant meaning to anything. Okay, but you could use these objects to simplify your life by choosing the right coordinate system in which there is a derivative missing. Uh, so that you can simplify gamma into an expression which looks like this. There is a partial derivative piece missing here. Okay, fine. So, using, nevertheless, even if this quantity is not a tensor, gamma, alpha, beta, gamma is not a tensor, one can construct a tensor out of that by differentiating with respect to coordinates. Okay, and this is our first definition of a tensor constructed out of derivatives of the metric. Remember, gamma itself contains derivatives of the metric, and this quantity, which is called the Riemann tensor, or alpha, beta, gamma, delta, is written in the following way. Okay, it's a partial derivative with respect to delta of gamma, alpha, beta, gamma, minus partial derivative with respect to gamma of gamma, alpha, beta, delta, oops, and times, disaster. Okay, give me a minute. Okay, so it will correct the whole thing later, but right now we have the equation right. Okay, so R alpha beta gamma delta is written as partial derivative with respect to x delta of gamma alpha beta gamma minus partial derivative with respect to gamma of gamma alpha beta delta plus gamma mu beta gamma gamma alpha mu delta minus gamma mu beta delta gamma alpha mu gamma. Okay, the error. Okay, so you can check one important thing here, and that is if you look at the first two terms, for example, of course, we'll see the last two also. If you look at the first two terms, then it is antisymmetric under the exchange of gamma and delta. It's a delta derivative of gamma alpha beta gamma minus gamma derivative of gamma alpha beta delta. So if you swap delta and gamma, this piece will change sign. Okay. Now, there is nothing special about this piece. If you look at the quadratic piece in gamma, that also has the same property. If you replace gamma delta by delta gamma, you will get this expression, but there is a relative sign between them. So the Riemann tensor has a property that with respect to gamma and delta, it is antisymmetric. Okay, so that is one important property that we should keep in mind. Okay, fine. So notice that although gammas themselves are not tensors, okay, this particular combination is a tensor. Okay, so of course you can check that if you look at the partial derivative of a non-tensor, that quantity is not a tensor. Okay, so individual pieces here are non-tensors. Okay, but that is okay. We don't care if individual pieces are tensors or not. What we care is this combination transforming as a tensor or not? And the answer is that the combination does transform as a tensor. So what you need to do is to determine the transformation property of uh, R alpha beta gamma delta uh, using the transformation property of the Riemann-Christoffel connection. Okay, so that transformation property is given right up here. Okay, which is also part of the exercise. But once you do that, then you know this. Okay, now notice that every time you want to determine any transformation property, you can always go back all the way to the metric and say that metric transforms like second rank covariant tensor or inverse metric transforms like second rank contravariant tensors and compute. But it's kind of pointless because if you have derived certain structures, then you might as well use the transformation properties of those structures to determine the transformation properties of the new structures which are dependent on these. Okay, so you have a primary structure defined in terms of metric, but once you construct a secondary structure like Riemann-Christoffel connection, and from which you construct the Riemann tensor, then once you derive the property of how Riemann-Christoffel connection would transform, that is good enough. You use that next time around instead of going all the way back to the metric. Now, of course, if you insist on going all the way back, the answer is not going to change. Okay, that fact should remain. Okay, so this is the first tensor that we have constructed, which is in some sense non-trivial. Non-trivial in the following sense that if you can try to construct any quantity out of this which is likely to be invariant under general coordinate transformation, then that quantity is not a constant quantity. It involves derivatives of the metric. Okay, contraction of the metric component did not give us anything interesting. Okay, so here are the quantities that you could construct using the Riemann tensor. Okay, so just pay attention to what is being done. So I have R alpha beta gamma delta. I have R mu nu rho sigma. Okay, and all I'm trying to do is to contract alpha with mu by taking G alpha mu, beta with nu by taking G beta nu, gamma with rho using this G, and delta with sigma using that G. Okay, so this quantity is quadratic in Riemann tensor, but the entire quantity is Lorentz scalar. Why is it Lorentz scalar? Because there is no free index here. Okay, all indices are summed, and therefore that therefore they would not the final quantity would not transform under general coordinate transformation. Since every object sitting in this expression is a tensor, this is some exercise that you have to do. It's a 1,3 tensor. This is a 1,3 tensor. This is a 0,2 tensor, and last three are 2,0 tensor. So if you can just check total transformation property of all of them turns out to be a scale. Okay, so this is one kind of uh, scalar, one kind of coordinate invariant that one could define. Go back to the metric that we were looking at, like flat Minkowski space or the metric on two sphere, and compute Riemann tensors for them and check what would be the answer. Okay, so this is one invariant. Okay, you could write down some other invariant. Okay, so for example, look at this invariant. This invariant is constructed from R alpha beta gamma delta by saying that gamma is same as alpha. Okay, that is like saying, that is like contracting this quantity by identifying just summing alpha and gamma simultaneously. Okay, then you are left with beta and delta, which you contract with the metric. Okay, so this is the quantity which is a scalar, and you could ask a question that would this quantity be useful quantity to distinguish different geometries. Okay, and of course, like this could also be useful. Or you could write down something more complicated where you have indices alpha contracted here and index gamma contracted here, and then beta delta and mu nu could be contracted using some metrics. Okay, now clearly you can easily imagine that the number of such scalars or number of such invariants that you can write down is infinite. Okay, we have written quantities which are linear in Riemann tensor or quadratic in Riemann tensor, but nobody stops you from writing quantities which are cubic, fourth order, or whatever. Okay, so total number of invariants that you could construct using Riemann tensor can be infinite in number, really. Okay, any questions at this point?
I mean, those infinite number aren't really independent of each other, right?
Well, they are not independent because Riemann tensor has only finite number of components.
Yeah.
Right. So if you want, you could just look at piecemeal every component of Riemann tensor. Then whatever are the number of independent component of Riemann tensor, that much information is available to you, really. Okay. So
Yeah.
only thing is that, like, you may find some invariant more convenient to use than some other invariant, and which one you want to use can be your choice. You may not want to use some 20th power of Riemann tensor. Okay, but you may want to use Riemann tensor with, I mean, quadratic or cubic maybe, right? That kind of stuff. Okay. If somebody comes and tells you that like 20th power of Riemann tensor is a simple expression, it will be kind of hard to believe, right? I mean, given that tensor itself has multiple components and therefore multiple kind of values that these indices would take, you wouldn't want to take 20th power of something and contract with G mu news to kind of try to evaluate this. Okay. So yes, in principle, you can construct any number of invariants, but the relevant ones are finite in number. Any other question? Okay, so if there are no questions, we can kind of go ahead and say, continue our kind of discussion as to how to compare quantities. So we can choose any of these quantities. Okay, pick two different metrics and see whether these invariants that we have constructed, whether they are same or not. Okay, and when when we say that they are same or not, this is something we said last time also, that if these invariants are different, then you are sure that the two geometries are not same. But if these invariants are same, then you are not sure that these geometries are necessarily same. Okay, because it is possible that one invariant could be same for two geometries, but the second invariant may differ. Okay, so therefore getting one particular invariant same doesn't solve your problem. You may have to kind of ask one more question or or few more questions until you kind of be sure that these two geometries are same or not. Okay. Now, of course, there is another way of trying to figure out whether the two geometries are same or not, and that is to find out coordinate transformation which takes you from one to the other. Okay, if you can figure that out, then you don't even need to do this. Okay, but the point of doing this is that finding a correct coordinate transformation which takes you from one metric to another metric is very complicated. It's a much more complicated problem than trying to determine these invariants. Okay. Of course, you can do a complicated general coordinate transformation on a given metric to produce a new metric. Okay, what is the endpoint of the metric? If it is already fixed, then it is often difficult to spot the general coordinate transformation. But if you fix a general coordinate transformation and allow whatever is the outcome of that, then of course that is an easy computation to do. Okay, so but what we are trying to do is that we are given two fixed metrics. Okay, and we want to know whether they are same or not. Okay, whether they describe same geometry or not, and that's why looking for such invariants. Okay, excuse me. So coming back to our problem, if you look at Minkowski space in any dimensions, okay, our metric would be just given by eta alpha beta, and eta alpha beta is independent of any coordinates. They are just numbers. Okay, and because it is independent of coordinates, the corresponding Riemann-Christoffel connection would just vanish. Okay, so let's kind of take a look at that. You would know it already, but given that Riemann-Christoffel connection is written in terms of derivatives of the metric, if your metric is has all constant entries, this whole stuff vanishes. Okay, so your connection, Riemann-Christoffel connection is 0. Once that is 0, then your Riemann tensor also would vanish, simply because Riemann tensor is gamma and its derivative. Okay, so therefore, if the Riemann tensor is 0, the Riemann tensor is 0, then all invariants that you would construct for Minkowski space would vanish. Okay. So now our problem has become simple, because if you look at any other geometry and in which if you find that there exists at least one invariant which is non-zero, then that geometry cannot be brought into Minkowski space form by any general coordinate transformation. Okay. Does that make sense? Is it making sense? That for Minkowski space, it doesn't matter in how many dimensions, 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, any dimension, the metric is like this. Okay, just diagonal minus 1, 1, 1, 1 kind of stuff, depending upon how many spatial directions you have. And in all such dimensions, Minkowski space has a property that every component of the Riemann tensor vanishes. We have written R alpha beta gamma delta is equal to 0 for any alpha beta gamma delta. Okay, no conditions on alpha beta gamma delta. Put anything that is allowed by the symmetries of the Riemann tensor, namely, as long as you keep gamma delta antisymmetric, this quantity just vanishes. So any other geometry, if you find that any invariant constructed out of Riemann tensor is non-zero, you know that you have a different geometry. Okay. So that is how we are going to kind of distinguish non-Lorentzian geometry, non-Minkowski geometry from Minkowski geometry. Okay. Fine. So here's an exercise. It's a little longish exercise, but it's kind of very instructive exercise. We know the metric G alpha beta for the two sphere. Okay. Remember, you can choose any coordinate system really. Okay. So remember, we had written down this metric, but I can show it to you. You can just go back a little to get. So you can choose this. Okay. So G theta theta was a squared. Okay. And G phi phi was a squared sine squared theta. So you can choose this metric. Nothing very special about it. If you are enterprising enough, you could choose this also. It doesn't matter really. Okay, it's just that this has off diagonal pieces in the metric and stuff like that. This is a quantity which is coordinate invariant, so it doesn't matter in which coordinates you compute this quantity. Okay, so given this form, okay, first thing that you notice compared to the Minkowski space metric is that your metric, remember, A is a constant. We are looking at a sphere of constant radius, so A is a constant, but nevertheless your metric depends on coordinates. It's a function of sine squared theta, for example, g phi phi. Okay, g theta theta is still constant, but at least g phi phi is a function of sine squared theta. So there is a good chance that your Riemann-Christoffel connection would be non-zero. Okay, in fact, it would be non-zero given the kind of form that you have, but you need to compute that, of course. Okay, so I think that was one of the exercises. Yes, not very sure. Maybe I didn't give that as an exercise. But anyway, you need to do that because, so you compute Riemann-Christoffel connection. You don't have too many components because you are working in 2 dimensions. Riemann-Christoffel connection has 3 indices, alpha, beta, gamma. So you have to allow alpha, beta, gamma, all of them to take value theta and phi. Okay, so there are multiple terms, but nevertheless you should be able to compute. Maybe I should tell you one more thing about the Riemann-Christoffel connection, which I did not tell you earlier. And that is, it doesn't matter where you look at it, but if you look at this expression for Riemann-Christoffel connection, then you see that it is symmetric in beta gamma. Okay, so if you exchange beta and gamma, this expression get exchanged, but there is a relative plus sign. So it is a symmetric under exchange of beta and gamma. Here, if you exchange beta and gamma, then g beta gamma goes to g gamma beta, but we know that the metric is symmetric. So Riemann-Christoffel connection has a property that it is symmetric in lower 2 indices. Okay, so that is something which will help you reduce computation of the number of components, because if you compute g theta phi, then you don't have to compute g phi theta because I mean, not g. If you compute gamma alpha theta phi, alpha could be anything, gamma alpha theta phi, then you don't have to compute gamma alpha phi theta because of this symmetry. Okay, so that is something which would kind of reduce computation of independent components of the Christoffel connection. Once you compute that, you need to plug this back into this quantity. Okay, here also again gamma delta components of the Riemann tensor are antisymmetric. So if gamma is say theta, then delta is phi. Okay, and then you don't have to determine what happens when gamma is phi and delta is theta, because they are related to each other by a sign. Okay, so so you can kind of figure out how many components of Riemann tensor that you need to compute. Okay. Okay, so so this exercise basically tells you that if you compute Riemann tensor and then you contract that with the metric on the sphere and inverse metric on the sphere. Inverse metric is not a very difficult quantity to compute. G upstairs theta theta would be just e to the minus 2, and G upstairs phi phi would be e to the minus 2 by sine squared theta. Okay, just inverting it. You just think of that as a matrix and find out the inverse of the matrix. Okay, but once you do that, then you can just plug that whole stuff in and compute that quantity. Okay, and you'll find that that quantity depends on this constant a in this fashion. It goes as a to the minus 4. Okay, and since you have a sphere of finite radius, I mean a takes some finite value, 1, 2, square root 3, whatever, that kind of stuff. Okay, this invariant takes non-zero value. Okay, because this, unless a is of course infinite. Okay, but that is kind of a very uh, special sphere that you would be really looking at, which is an infinite radius object. For any finite a, this quantity is non-zero. Okay, as against the Minkowski computation, that quantity, since Riemann tensor is 0, all quantities constructed out of Riemann tensors would be 0. Okay, so this is one indication that and this is of course a clear indication that the metric on S2 is different from metric on any dimensional Minkowski space. For example, two-dimensional Minkowski space metric is different from two-dimensional sphere space metric on two-dimensional sphere. Okay, so therefore there cannot be any coordinate transformation which can bring this metric to a flat Minkowski space metric. Okay, fine. So we therefore conclude that S2 is not a Euclidean geometry. Okay, and different values of A correspond to different geometric spaces. Now remember that we were saying that these are general coordinate transformation invariants, right? So if you look at a sphere of radius 1 versus a sphere of radius 2, then this invariant for sphere of radius 1 would be about 1, whereas this invariant for a sphere of radius 2 would be 1 over 16. Okay, and since those numbers are different, a sphere of radius 2 and sphere of radius 1 cannot be transformed into each other. Okay, so although they look like spheres, they are of different size, of course, but you know, geometrically they look the same. Okay, you cannot transform them into each other. Okay, okay, so we have seen one thing already, that the derivative of the tensor does not transform like a tensor. Okay, right? This is the thing that we have seen when we studied derivative of the metric, right? Metric was a second rank covariant tensor. We took its partial derivative and we found that that doesn't transform like a tensor. Okay, fine. So therefore, what we could do is to define a new quantity, new kind of derivative, which will ensure that when you take a derivative of a tensor, it still returns you a tensor. Okay. So remember what we have done is this. We have taken a partial derivative. Okay. We took a partial derivative and we found that partial derivative of metric, okay, does not, so metric is a tensor, but partial derivative of metric is not a tensor. Okay, so the operation of taking a partial derivative of a tensor does not return a tensor. Okay, that's the typical transformation property. Fine. So you could ask a question that like, okay, can I modify the derivative such that a new derivative acting on a tensor will return a tensor again? Okay, that tensor may have a different what is it called? That tensor may be of different rank. Okay, but nevertheless, you should be able to at least get a Riemann. You should be able, at least be able to get a tensor under the transformation. Okay, so what we are going to do is to define a new object called a covariant derivative. Okay, this covariant derivative is similar in spirit as the covariant derivative that you would use in, say, quantum field theory or even in quantum mechanics, where you replace partial derivative excuse me, partial derivatives by what are called minimal couplings, where you replace del mu by del mu minus IEA mu kind of change. That new derivative that you get is typically called a covariant derivative, and that's what we will do. We'll define a covariant derivative, and so here's a complicated definition, but it's not very difficult to understand. So let's kind of run through the terms here. So here's a covariant derivative, and this covariant derivative acting on a tensor of contravariant rank K and covariant rank L acts in this fashion. Okay, so it contains, of course, a partial derivative, and the partial derivative acts exactly the way the partial derivative would have acted on any tensor. So that doesn't require much discussion. But then, in addition to that, the covariant derivative contains a term which involves a Riemann-Christoffel connection, and it comes with plus sign whenever you exchange the index on the tensor which is contravariant. Okay, so if you replace alpha 1 by gamma 1, okay, now notice alpha 1 and gamma 1 are there in the Christoffel connection. So Christoffel connection is alpha 1, alpha, gamma 1. Alpha is the index coming from covariant derivative, and then you pull an index from the tensor alpha 1, put it on the Christoffel connection, and the index from Christoffel connection is gamma 1 is kind of replacing alpha 1. Okay, if you do this, if you are replacing the contravariant index, it comes with plus sign. Okay, you can do it for every such index. Okay, and you can go all the way from alpha 1, alpha 2, alpha 3, dot dot dot, all the way up to alpha k. So there are k such terms where gamma is replacing alpha 1 by gamma 1, alpha 2 by gamma 2 in the tensor, one at a time. And if the tensor has covariant indices, then it would replace the covariant indices with minus sign. Okay, so it is minus gamma, it will replace beta 1 by delta 1, beta 2 by delta 2, dot dot dot, all the way up to beta L replaced by delta L. Okay, so this is a general definition. You don't have to kind of memorize it. What is required is for you to remember is that Riemann-Christoffel connection would exchange contravariant index with a positive sign and would exchange covariant index with a negative sign. That is the only thing that you really need to remember. Okay, and also of course, you need to remember that the covariant derivative itself comes with the covariant index. Okay, and not the contravariant index. Okay, now the word covariant is a bit of an unfortunate thing in the sense that this covariant I mean, this covariance is different from the covariant index on the derivative, although thankfully we do write covariant index on it. But this word covariant implies that under general coordinate transformation, this object is going to transform covariantly. Okay, in that sense, it maintains the covariance under general coordinate transformation. Okay, and that is the reason why the word covariant derivative, and not so much for it actually carry a covariant index. Okay, any questions about this? So I should say at this point that like you need some practice to kind of get used to this kind of these kind of manipulations, particularly like if you want to take covariant derivatives of tensors and so on. First couple of times you may find that it is complicated, but after some point it will just fall in place. All you have to remember is that when a covariant derivative acts on a tensor with arbitrary rank, say KL, this thing, gamma will appear k plus L times. Okay, with gamma multiplying tensor with appropriately exchanged indices. If it is contravariant indices exchange positive sign, covariant indices exchange negative sign. Okay, so nothing very difficult really. Okay, of course, one really doesn't work with the tensors with like arbitrarily large indices. You do work with tensors with like maybe two covariant, two contravariant, or maybe four covariant indices or some such thing, but that's pretty much that you would really want to do. Okay, fine. So here is an exercise where you have to, of course, utilize certain properties. First property that you want to use is that T alpha 1 dot 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 alpha k beta 1 dot 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 beta L itself transforms as a rank k comma L tensor. Okay, now that is the input. Okay, there is nothing like you don't have to derive that because there is no way of doing that. That is just definition. Okay, so once you kind of assume that this transforms like a k comma L tensor, then with this definition, you need to show that d alpha acting on T alpha 1 dot dot alpha k beta 1 dot dot beta L transforms like k comma L plus 1 tensor. Okay, that means k contravariant and L plus 1 covariant indices. Okay, now two inputs required. One input is of course that T itself transforms like k comma L index, and the second input is how the Riemann-Christoffel connection transforms. Okay, So that information is already there with you. Okay. So these two are inputs. How the partial derivative acts on t is something we know. If you do a general coordinate transformation, then this partial derivative is going to generate a inhomogeneous term. This is something that we kind of talked about just before we defined the covariant derivative. So we know that there is an inhomogeneous piece coming from here, and whatever is the inhomogeneous piece that you are going to get from this term, all these other terms have to conspire to cancel that. Okay. So you need to check this particular exercise. Okay. So I would suggest you could do this exercise by keeping, say, one covariant and one contravariant, or one covariant and two contravariant indices, like keep beta 1 and alpha 1, alpha 2, something like that. Okay. And get an idea as to how it works. Then you can generalize it to arbitrary k and l. Okay. Because generalizing it to arbitrary k and l is just writing more and more gammas, but transformation properties are kind of easy to read out. Okay. Any questions here? So I must say that the exercise is straightforward, but it is not like a two-line calculation. It would require you to kind of make the page a bit dirty, but at the end of the calculation, you will see several terms just cancel out and a nice looking object survives. Okay. And but it's a good exercise to do. Any questions about this? Okay, if not, let's go ahead. Okay, so now remember that we know that partial derivative of the metric is not a tensor. Okay, so and then I said that, like, okay, we cannot construct any tensorial quantity by using partial derivative of metric, and that is the reason why we wanted to go to second derivative of the metric by writing derivative of the Riemann principal connection and stuff like that. And then we wrote down Riemann tensor. Okay. But I just gave you a definition of what is called a covariant derivative, which when acts on a tensor, returns you a tensor. Okay. Now, given this definition, we can go back and ask the question that how can we make a statement that derivative of g alpha beta can never give you a tensor? Okay, partial derivative, no. But what about covariant derivative? And naively, of course, you would say that, like, okay, if g beta gamma is a tensor, then d alpha of g beta gamma is a third rank covariant tensor. Okay. And of course, it is true because that is how the covariant derivative is defined. Okay. So it's one more exercise. You check that d alpha of g beta gamma is identically zero. Okay. By identically zero, I mean that you just plug in the expressions of the covariant derivative. That means del alpha of g beta gamma minus, remember, covariant indices come with minus sign, right? Whenever you exchange a covariant index, beta 1 is replaced by delta 1, it comes with minus sign. Whereas alpha 1 is exchanged by gamma 1, it came with plus sign. So look at the minus sign pieces only because our tensor is only covariant tensor. Okay. So use the definition that we have given. Okay. If you want, I can give the definition right here. Okay. Use this definition and check. And then, of course, you know what is the form of the Riemann principal connection written in terms of partial derivative of the metric. Okay. Plug in that expression. Okay. So you have a lot of pieces. One piece is partial derivative of g beta gamma with respect to x alpha. And then there are two pieces coming from gamma times g and the gamma times g. Okay. For each one of these covariant indices. There are two gammas sitting around. Substitute those, replace those gammas by their definition written in terms of g and its derivative. Okay. And simplify the expression. You will find that the answer is, you should find that the answer is identically zero. Meaning of this statement is that this means that no matter what is the choice of your metric, it doesn't matter whether the metric was flat, whether the metric corresponds to some curved space, whether the metric has a lot of non-trivial terms appearing in different components. This statement is true independent of composition of the metric. Okay. And if that is the case, then you really cannot use this tensor for determining any quantity because it's going to be zero all the time. Okay. This statement, you may find some books would state this as covariant constancy of the metric. Okay, so one typically says that the metric is covariantly constant. Okay, that means a covariant derivative acting on it gives you zero answer. Okay, so if you try to integrate this equation, it will tell you that with respect to covariant derivative, g is just a constant. Okay, fine. There are a couple of caveats I should mention, because if you look at different books, you may get different expressions. So maybe I should kind of mention this. The definition of Riemann-Christoffel connection that I gave you is uniquely defined. You know, it doesn't matter which book, which review article, which lecture notes you look at, that is the definition. There is no confusion there. But Riemann tensor, you may find it defined differently in different places. Different books have different conventions. Of course, different books also have different space-time signature. So I have chosen a convention where the last index derivative comes first and second last index derivative comes later. And of course, there is a relative sign. That relative sign is, of course, a fact that is that you will see in every expression, no matter which book or article that you look at. But you may find Riemann tensor defined by del gamma of gamma alpha beta delta minus del delta of gamma alpha beta gamma. It is possible. Okay. So what is important here is to fix your convention and stick to that convention all the time. Halfway through, if you switch from one book to another, you may not get answers right. Okay, because if you swap these, of course, you will also swap that. So if in one computation you get this component to be positive, and halfway through, if you change your convention, then instead of getting positive answer, you will end up getting negative answer. Okay, and that is the reason why it is important to kind of stick to a particular convention and do the computation consistent with that convention. So many times you see articles written on certain kind of computations would define their notation and convention right in the beginning, and everything that follows after that is supposedly consistent with the convention that they have chosen. Okay, so if you find somebody else writing del gamma of gamma, capital gamma alpha beta delta first and this quantity later, don't panic. That is just a choice of convention. Okay, so there are non-unique ways of defining these quantities, but the property that the Riemann tensor is antisymmetric in gamma delta is universally true. Okay, so fine. So let's go down to what we are doing. So yeah, I just want to keep this. And so this is a kind of simple exercise, and this exercise also tells you that if you did not know what Riemann-Christoffel connection was, then the covariant constancy of the metric would tell you exactly the expression of what of the Riemann-Christoffel connection. So to put it a little differently, suppose you just formally write down, use this definition of the covariant derivative, and formally write down d alpha of g beta gamma in this way. That means you write down that as del alpha of g beta gamma minus gamma alpha beta, say sigma g sigma gamma minus gamma alpha gamma rho g beta rho equals 0. Write down an expression like that. Okay, and suppose you don't know what is that gamma. Okay, you use this equation. Okay, permute alpha, beta, gamma indices in appropriate fashion. Add the two terms and subtract the third one. Okay, you know which terms to add because it is symmetric in beta gamma, so you have to add terms where you have swapped beta and gamma in the expression, but subtract the term where you swap alpha with one of the pieces. Okay, and you can check that whatever expression that you would get would exactly reproduce the formula that we have written down for Riemann-Christoffel connection. Okay, namely this. Okay, you should be able to recover that. Okay, so that's not an exercise, but if you are curious, you can kind of do that. Just take this equation, write formally, say I don't know what gamma is, but for any gamma constructed out of G, this statement is true. Let me reconstruct gamma using this equation, and you should be able to do that. Okay.
Sir,
Any question? Yes.
one way to see this could be to go to local inertial frame, right?
Yes, but that
Yeah,
is true. Of course, you could do that. But if you go to local inertial frame, it doesn't tell you anything about the metric. It tells you only what happens to the metric locally. Right?
yeah, but Christoffel symbols all vanish.
That's right. Yeah.
Yeah, so this
so just,
covariant derivative will
no, then the covariant derivative tells that ordinary partial derivative of G is 0. Right? Right? That just tells you that locally you can make the metric constant. We will do that soon.
also, sir, this conventions of Riemann tensor, is it only because we are finally concerned with the scalars, whether
No,
it's
no,
6 or minus 6?
no, no,
It
no, no.
doesn't
It
matter.
is not like that. It's just a matter of convention. It's like, I mean, I don't know how to say this. That I mean, it is not so important as to how these components are defined. Okay, how R alpha beta gamma delta is defined. Okay, in the sense that like, uh, uh, yeah, I mean, I don't know how to say this, but uh, I mean, it's kind of purely conventional stuff. It's not because we are really looking at only the invariants. The invariance that we are looking at is only here, but you may be writing down an equation which is a tensorial equation. Okay, but if you have an overall sign coming into that tensorial equation, then it doesn't affect the physical result. Okay, so any equation which involves a Riemann tensor on one side and a Riemann tensor on the other side, then it doesn't matter really. Or if Riemann tensor on one side and the zero on the other side, then it again doesn't matter whether somebody's definition had a delta derivative first or gamma derivative first. Okay, so that it is like that. It is not so much about what happens to the invariants. Okay, in fact, sometimes the invariants could flip sign. So, for example, if you try to construct a scalar, linear scalar quantity, which is one of them that we have written down recent here, are just a sec. This one. Okay, so if you swap these variables, then this quantity could be positive in one convention and negative in another convention. Okay, and but it doesn't matter because in one convention you would say that like if this scalar is negative, then the space has a particular kind of curvature. In the other convention, it will say that if this quantity is positive, then it has the same kind of curvature. Okay, so within the definition, so like if this invariant was positive, I would say it is a positive curvature space. Okay, if somebody uses a different convention, then that fellow will say that whenever this is negative, the space is positive curvature. Okay, it can happen. Okay, but as long as the statements are consistent, it is fine, I think. So there are books which use the reverse notation for reasons of their own, but it doesn't matter really. Okay.
Okay.
But you don't have to look at the invariant. In fact, if you look at the equation, which is typically tensorial equation, even there it shouldn't matter. Any other question? Okay, so if there is no question, we can kind of ask a reverse question. Okay, so we have kind of created a criteria which allows us to distinguish uh, geometries which are different from Minkowski geometry, for example, Minkowski space, uh, by showing that there exists some curvature invariance. Remember, Riemann-Fritz tensor is also called a curvature tensor. It's a measure of curvature in of space-time. So, if the curvature invariants of the space-time are non-zero, you know that those geometries are different from the Minkowski geometry. Okay. So we can now ask a reverse question. Suppose somebody gives you a metric, and which looks quite complicated. Okay, you want to know how close can we bring that metric to a Minkowski space metric. Okay, and as Aman was saying some time ago, that of course locally you can bring any metric to Minkowski form by general coordinate transformation. Okay, so let's kind of see how we could do that. Okay, so consider the point P, whose local coordinates are x0 alpha, okay, and let x alpha prime be coordinates of a point in the small neighborhood of this point. Okay, so x0 alpha is a coordinate of a point. Is there a question?
So is prime on the alpha or on the x?
Sorry.
Is prime on the alpha or on the x?
Well, I should have put prime on the x also, but I am not putting a prime on the x because I am using the local coordinates defined at the point. Okay, but the coordinates that I use at a point in the neighborhood, I could use a different choice of variables. So imagine like x0 alpha, that alpha is Cartesian, but x alpha prime, that alpha prime is some polar coordinates. Okay, but it's in the neighborhood of it. Okay, so I just want to make a distinction there. Okay.
Yeah, okay.
So then what you're doing is that you are using this coordinate, writing that in as a kind of Taylor series expansion around a point x0 alpha. Okay. So one thing is that you kind of relate it to the original coordinate system. This statement of delta alpha prime beta is just to say that uh, the local orthogonal frame defined at x0 alpha and the local orthogonal frame defined at a new point, it is still an orthogonal frame, so you can kind of to first order can just match. Okay, but then at the next order you have a correction to it. Okay, so there is a matrix which would kind of tell you how you would relate these two coordinates. Okay, and that quantity, now remember, you should be actually writing x beta prime here, but x beta prime is to be determined at x0 point when you take a derivative, and therefore you basically just write down x beta here. Okay, so you can write down this as a derivative defined at that point, which is of course a constant quantity because it is defined precisely at one point. Okay, so it just tells you slope of the line at that coordinate. Okay, so you can use this and convert the tensorial transformation property of the metric into a similarity transformation of the metric. Okay, so locally you do this as a similarity transformation. So in a matrix form, you can write it in this way. So alpha beta component is the alpha beta component of the similarity transform metric. Okay. So now we can ask a question: what kind of choice of basis I make, say that some rotation or some scaling or some choice of relation between the basis vectors of one coordinate system to another coordinate system, such that I can diagonalize the metric. Okay, we know typically if you do a similarity transformation, you should be able to diagonalize a matrix. G alpha beta is a symmetric matrix, okay, and has a non-vanishing determinant, so it should be diagonalizable in principle, at least locally. Okay, so so we of course know that at any given point we have orthogonal coordinates defined using the basis vectors of the tangent space. Okay, and because you have this orthogonal coordinate system, you also have orthogonal symmetry, which rotates these vectors, rotate the basis of the tangent space. Okay, so we can use this orthogonal transformation to diagonalize G alpha beta at this point. Okay, fine. So there may be a orthogonal transformation which will bring this into a form with some eigenvalues lambda 1 dot lambda 4. Okay, now there is no reason why these uh, numbers should be exactly same as what the Minkowski space numbers would be, but at least they could be brought into this form. Okay, only thing is that given that the metric G has a Lorentzian signature, tells you out of these 4 lambdas, at least one of them has to have a negative sign. Okay, so one of the lambdas is negative. So we could choose, say, lambda 1 is negative. Okay, so if you do that, then you can write down S in the following way. You choose S to be a matrix which is O transpose times square root of minus lambda 1. Remember, lambda 1 is negative. I mean, that is a choice we made. Square root of lambda 1 inverse dot square root of lambda 4 inverse, sorry, square root of minus lambda 1 inverse. Okay, if you choose your S to be this, then the metric G can be brought into a Minkowski form. Okay, so locally it is always possible to find a similarity transformation to convert any metric and bring it into a Minkowski form. Okay, so it of course requires doing some kind of rescaling. Pure orthogonal transformation wouldn't do that. Okay, but that is something we know, because orthogonal transformations always maintain the length of the vector fixed. Okay, it can rotate the vector but cannot change the length of the vector. So you need a transformation which will appropriately scale it down or up to bring it to a form of this kind. Okay, but this is the convention that we have been using, that time component is negative and space component is positive. So thus we see that there exists a coordinate transformation which brings any metric to a Minkowski metric at a point, okay, or in an extremely small neighborhood of a point. Okay, locally it can be brought into a Minkowski form. Okay, so any questions about this? So this statement is essentially a statement of equivalence principle, that in a sufficiently small neighborhood, you shouldn't be able to distinguish a flat space and a curved space in the sense that, like, if you look at accelerated frame versus acceleration due to gravity, you shouldn't be able to distinguish those. Okay. Any questions? Okay. If not, then let's go back to the geodesic.
Sir,
Yes.
we must have an extra freedom, right? Because we can still do Lorentz transformation then.
That is right. Yeah. So we will do.
Yeah. So
yeah.
there would.
So in this similarity transformation, you could also add a Lorentz transformation piece also. Okay. But Lorentz transformation leaves eta invariant.
Yeah.
Okay. So you can have a O transpose times this scale piece times lambda, where lambda is a convention we have been conventionally using as Lorentz transformation. Okay.
Okay.
So of course that is something I did not write, because we know that eta is left invariant by Lorentz transformation.
Yes.
So yes, there is a redundancy of that in writing S. Any other question? Okay, so maybe we can go over to the discussion of geodesic again. So remember, we have already written down the geodesic equation, and we started off uh, with a straight line equation or a free particle equation in Minkowski space, and then we did an arbitrary general coordinate transformation, and then we said that, like, if we want the equation to be form invariant, then what should be the conditions on the terms that are written down in the equation under general coordinate transformation. And that is how we actually showed that the free particle equation written in the Minkowski space was not form invariant under general coordinate transformation. But whatever new equation we got, we converted that equation into by writing one of the p's as gamma, and then we defined the transformation property of gamma such that the equation remains form invariant. That is how we derived the geodesic equation. Okay, but in reality, geodesic equation is a shortest is a statement about finding a path which is a shortest path from point from an initial point to a final point. Okay, in the Euclidean space or in the Minkowski space, that shortest path will of course be a straight line. Okay, but if you are looking at the curved space, then that shortest path, at least prima facie, doesn't look like a straight line. Okay, so let us do the following thing. Suppose we have a curve which starts at point x1 alpha and it ends at a point x2 alpha. Okay, uh, and we parameterize that path, okay, by a parameter lambda. This lambda takes values between 0 and 1. Nothing very special about it. You could have taken it from 0 to some other value also. It doesn't really matter. But if you choose some range, then one end of that range, that is lambda equals 0, x alpha at lambda equals 0 is x1 alpha, and x alpha at lambda equals whatever is the other limit, 1 in this case, to be x2 alpha. So these are the two endpoints of the path that we are looking at. Okay. Then you can define the length of the path to be just integral of the proper time. Okay. So proper time is the one which kind of evolves along the path, and you define the length of the path to be that integral. Okay. But you can convert this proper time using the fact that d tau squared is g alpha beta dx alpha dx beta. You can convert d tau as square root of this quantity, and since we are parameterizing x alpha in terms of lambda, you can kind of convert this integral into an integral over lambda. Okay, so your length of the path is determined by doing an integral of this kind, where g alpha beta is a metric and lambda is a parameter which parameterizes the curve that you are looking at. Okay, fine. Now, if I want to look at the shortest path, then you take this definition. Okay, you take the definition and you want to extremize the length. Okay, you want to actually minimize the length. So what you do is that you look at the variation of this length functional, okay, and study that variation. Okay, so you want to say, if I say look at some delta x alpha, then what is the variation in L? Okay, so remember this is a quantity. You have variation here, variation there, as well as variation in G. Okay, these are all three. These are the places where the coordinate x is sitting around. So you get the expression. When you do a variation of square root, it of course gives you a kind of the same quantity to the minus half power. Then you have terms like a variation of coordinate inside G times these two pieces plus 2 times variation of this coordinate, okay, and d by d lambda derivative of that variation. Okay. Now the factor of 2 is written because we know that g alpha beta is symmetric. So therefore, if you do a variation of x alpha versus you do a variation of x beta, they would give you the same expression. That's why the factor of 2. Okay, under exchange of dummy indices. Okay. The reason why I have switched to mu nu indices here is because the usual convention, Einstein summation convention, is to not repeat indices more than twice. Okay, so we have already summed alpha beta here. So although these are kind of derived from the same g alpha beta dx alpha dx beta piece, you cannot repeat these indices again. So that's why mu nu and rho. Okay. So that is just to be consistent with the Einstein summation convention. Okay. So what we will do is we have this d by d lambda piece sitting around here acting on a small variation. What we want to actually do is to pull this variation piece out. So we will do an integration by parts. Okay. When you do integration by parts, it acts on multiple pieces. There's a piece sitting around outside also, and then there are these G mu del x2 pieces also sitting around. So we will kind of carry out that exercise. So just pay attention. Let me just go down and keep that equation for you. Okay, so here's the equation. So the first term here in the first row, the first term in the curly bracket is the quantity which is same as the quantity in the first row here. Okay, we haven't done anything to that. Okay, the second term in the curly bracket, okay, is a term where integration by parts acts on g mu nu times del x nu by del lambda. Okay, that is the piece. Okay. Now, because you are doing integration by parts, it would flip sign. That's why there is a minus sign. The other term for the integration by parts is when d by d lambda acts on this piece, which is outside the square bracket. Okay, and that is the piece written out here. Okay, so in that case, you see a delta x rho. I have changed the index for convenience so that I can pull a delta x rho common from everywhere. So anyway, that index was summed, so it was dummy. Times g rho sigma del x sigma times del dd lambda of whatever was the quantity sitting outside. Okay, fine. There is no factor of 2 here because this 2 and this half would cancel. That's why there is nothing sitting around there. Okay, are you with me on this?
Yeah, yes.
Okay. Okay, so what we'll do now at this point is to choose the lambda parameterization in such a way that g alpha beta dx alpha by d lambda dx beta by d lambda is constant. Okay, that is the kind of parameterization we will choose. Okay, if you do that parameterization, okay, that parameterization is just the following statement that if you look at equal intervals in lambda space, the parameter space, if those equal intervals in lambda correspond to equal distances in x alpha space, then you would get g alpha beta dx alpha dx beta to be constant. Okay, that is the statement. Okay, but if you do that, then yeah, so maybe I should just keep this. If you do that, then you will notice one interesting thing, that in our expression here, the second term, which involves d by d lambda of g mu nu dx mu by d lambda dx mu by d lambda, this piece will drop out because this quantity is constant and therefore d by d lambda of that is 0. Okay, fine. So once you set that to 0, then you are left with the expression, which is only an expression in the curly bracket multiplied by this piece outside. Okay, the third term here is completely vanished. Okay, so now there is a small exercise that you can do, that this expression inside this curly bracket is reproduced here again. Okay, this you can manipulate. You can of course pull delta x rho out common from all of them, but you can kind of write this expression by taking d by d lambda in. One term is very easy to see, which is the second derivative of x nu with lambda, and then there is a other term where d by d lambda acting on g. You can show that that piece plus this piece gives you an expression like that. Okay, this is times g mu rho times delta x rho. Okay, is that okay? So this is a kind of, you have to do some small manipulations of these quantities and collect the pieces correctly. Okay, that is all. Fine. So what we are going to do is utilize the results of this exercise. We'll assume that this is actually true. Okay, well, not assume, it is possible to show. but we will use this result, okay, and substitute this inside this curly bracket. Okay, so instead of writing this expression which is sitting in the curly bracket, we write down this expression in. This piece is 0 anyway. Okay, so we get delta L is written as minus sign, of course, because we got this with a minus factors. I write down a minus sign, which is not very important for us. Integral over d lambda times this half times g alpha beta dx alpha dx beta kind of piece to the minus half. Then there is a piece which is then there is a piece which is delta x rho g nu rho times this piece. Okay. Now, if you want to extremize this, that means delta L is 0, then you want to do it for arbitrary variation of x alpha, then you have no choice but to set this quantity to 0, because you cannot set the metric to 0, and this quantity is already set to a constant. Okay, so therefore you get this equation, which is of course our familiar geodesic equation. Okay, so now we have derived the geodesic equation from geometry by defining a line element based on the metric, and then we said that if we extremize the path going from point x1 to point x2, okay, what is the shortest path connecting these two? By extremizing this length functional, we derived the geodesic equation. Okay, so it's yet another derivation of the geodesic equation. So what we'll do is we'll stop here and we'll study the solution to geodesic equation in the next class. Okay. Any questions?
So how does one know that this is shortest path? This will give you shortest path because we are only extremizing, but
that is right. So, yeah, so if you want, you could do a second derivative and kind of set it to positive to get the shortest path. But typically geodesic could also give you a longest path. Okay, but longest is a kind of weird thing defined, because longest path makes no sense, right? So therefore you need to check that second derivative is positive.
okay, but actually in a circle, on a surface of a sphere,
yeah,
if you take 2 points,
yeah,
then both the great circles are geodesics, right? The
both the
close
great
ones
circles.
and one coming from behind.
Yeah, certainly. But the point is that,
Yes.
like, yeah, but the point is that it's really not a longest path still, because longest path is any, I mean, you can draw a very complicated shape object, right? Okay. You have to, of course, show that it solves this equation. Okay. So, yeah, I understand what you're saying. You're saying that, like, on the equator, if you took 2 points, then there is a short path and there is a long path going along the equator, for example. Okay.
Yeah.
Both of them are solution to this equation. True. Okay. So of course, when you say shortest path, you need to do next variation and show that that variation is positive.
That variation will come out to a positive even for the other path, because for a small deviation, the value always increases. The path always like increases.
For that variation, yeah, probably that's true. I'll have to check.
I mean,
yeah. No, actually, it would be true, but yeah, but
Yeah,
both.
that is also local minimum basically.
Yeah. But that is, yeah, I agree. Both of them are local minima in that sense. But that is not very surprising, right? You're solving a second order equation, so you would be getting 2 solutions, and both of them are extrema of the same type. But you could look at a path which is not the shortest path and try to see whether it solves. Okay, and clearly it wouldn't, because you want to set delta L to 0, really, right? I mean, you want to say that the variation is minimized. Okay. So yeah, I
So,
agree that
yeah,
the longer route also is a solution. Yeah, please.
when we talk about, say, twin paradox,
Yeah.
then uh, this this is maximized, right? Not maximized. I mean, we don't take the smaller solution
Yeah, yeah,
because
yeah. That
because
is
this
true.
is, yeah. So I I don't
Yeah.
understand why we call it shortest. I mean, we should not, right?
Well, it's not really important. What is important is that you kind of set the variation to 0. Okay, one way. Okay, so I should have used the word extremize if you are really harping on word. But
No, no. I suggest to use straightest because this is really generalization of that.
no, not necessarily. I mean, locally every path is straight.
Yes, but
I mean, how is it that like any curve that you draw on the surface of the sphere is not straight locally, right?
yeah,
So
but geodesics are the straightest ones.
no, but there is
I
no
mean,
notion of straightness at all, right? If there was a notion, then you would have defined it right using the straightness of path, right?
yeah, okay.
So because there is no notion, we define it through extremization condition. In fact, like, for one metric, you could kind of try to make some statement. You do a general coordinate transformation, you write on a equivalent metric, which is just related to the original metric. You wouldn't even know whether this is really a straightest object. Just take Minkowski space and do a horrendous uh, uh, general coordinate transformation, right? And you know, you won't be able to figure out what happens, right? The new coordinate system, new metric that you would get is so complicated that you wouldn't even know that it's Minkowski space, right? So straightness, if it was possible to define, you wouldn't even define a geodesic.
Okay.
Any other question?
So,
Yes.
using geodesics, can we define globally distance between any 2 points?
Globally?
Let's say on a sphere, we can do this. We can between any 2 points, we can find the geodesic and we can calculate the length of that geodesic,
Yeah,
and that in some sort will give us the distance between 2 points.
that is right. Yeah.
Can we do it always for other surfaces as well?
Yeah, yeah, of course. Because that is completely determined using the metric, right? Once you define a metric on the space, you should be able to define a notion of distance. Okay.
Okay, I mean, there always exists a unique geodesic that gives us minimum distance between 2 points. Uh, to define distance consistently, we should have a unique geodesic, right?
Yeah, but like you may not have unique geodesic all the time, right? I mean, like for example, uh, if you want to go from North Pole to South Pole, there is no unique geodesic, right? I mean,
Okay, yeah.
so of course in those cases, yeah. But like if you take sufficiently small region, then you have kind of unique solutions.
Okay.
But if you take polar points or some such thing, it's kind of difficult then.
Hmm. Yeah.
Any other question? Okay. So if there are no questions, we could